അപ്പൊ എന്തുകൊണ്ടാണ് ഈ TMS ഹൈഡ്രജൻ റെസൊണേറ്റ് ചെയ്യുന്ന പൊസിഷനിൽ നിന്നും മാറി നമ്മുടെ കോമ്പൗണ്ടിലുള്ള ഹൈഡ്രജൻസുകൾ റെസൊണേറ്റ് ചെയ്യുന്നത്? അല്ലെങ്കിൽ എന്തൊക്കെ തരത്തിലുള്ള എൻവയോൺമെന്റൽ പാരാമീറ്റേഴ്സുകളാണ് ഈ കെമിക്കൽ ഷിഫ്റ്റിനെ ഡിസൈഡ് ചെയ്യുന്നത് അല്ലെങ്കിൽ ഇൻഫ്ലുവൻസ് ചെയ്യുന്നത്? പ്രധാനമായിട്ടും രണ്ട് തരത്തിലുള്ള ഇഫക്റ്റുകളാണ്. ഒന്ന് ഡീഷീൽഡിങ്, മറ്റൊന്ന് മാഗ്നറ്റിക് അനൈസോട്രോപ്പി. ഡീഷീൽഡിങ് തന്നെ രണ്ട് തരത്തിലാവാം. ഡീഷീൽഡിങ് ബൈ ഇലക്ട്രോനെഗറ്റീവ് എലമെന്റ്സ്, അതുപോലെ തന്നെ ഡീഷീൽഡിങ് ബൈ ഹൈഡ്രജൻ ബോണ്ടിങ്. And another factor is anisotropic fields due to pi bonded electrons in the molecule. So we will discuss these factors in the coming session. If we look into the table, the hydrogens present in different environments has different chemical shift values. See the equation to calculate the resonating frequency of H1 or any other NMR active nucleus. That is, nu is equal to gamma by 2 pi B0 into 1 minus sigma, where gamma is the gyromagnetic ratio, B0 the applied field, and sigma the shielding constant. That is, the resonance frequency depends on gamma, B0, as well as the shielding constant sigma, that is the molecular environment of that particular nucleus. Actually, this dependence of nu on structure is the ultimate reason for the importance of NMR spectroscopy in organic chemistry. We know that the electron cloud that surrounds the nucleus also has a charge, motion, and hence a magnetic moment. This magnetic field generated by the electrons alters the B0 field in the microenvironment around the nucleus. Therefore, the actual field present at the given nucleus depends on the nature of the surrounding electrons. This electronic modulation of B0 field is termed as shielding. Therefore, the actual field at the nucleus, that is B effective, is different from the applied field. This variation of the resonance frequency due to the electronic environment of the nucleus under study is termed as the chemical shift. So the decreased shielding this results in a higher resonance frequency at a given B0 value, since sigma enters the equation after a negative sign. So now let us see what are the different parameters which controls the resonating frequency of various hydrogen nuclei present in the given molecule. The most important parameter is the presence of electronegative elements. Let us consider the hydrogen carrying carbon attached to an electronegative chlorine atom. So the presence of chlorine, an electronegative element, will inductively withdraw the electron density from carbon, which in turn withdraws the electron density from carbon-hydrogen bond. So the electron density around hydrogen nucleus is now gets reduced. That will reduce the shielding of electrons. Shielding of magnetic field, external magnetic field by the surrounding electrons. See the given chart. Let us consider the model compounds CH3X, where X stands for different electronegative elements. If you put X as fluorine, the most electronegative element, the chemical shift value of those hydrogens, CH3 hydrogens, is nearly at 4.26. If we change fluorine with oxygen, the value is nearly 3.4. Like that. If we replace X with silicon, carbon and silicon, almost close electronegativity values. And we arbitrarily put it as 0 for tetramethyl silane. So as the electronegativity of X atom increases, it will again and again reduce the electron density around the hydrogen, and that hydrogen gets thus de-shielded. So when we move from X equal to iodine to X equal to fluorine, the chemical shift value shifted from 2.16 to 4.26. Now let us consider the cumulative effect of electronegative atoms in a given molecule. Consider chloromethane CH3Cl, which contains only one chlorine. Therefore, the hydrogens report at 3.05 ppm. If we add two chlorines, it's an added effect. The chemical shift value shifts to 5.3 ppm. If you consider chloroform CHCl3, the chemical shift value is at 7.27 ppm. And usually this value considered as a secondary standard in NMR experiments, because usually we use CdCl3, deuterated chloroform, as a solvent for conducting the NMR experiments. And if it contains little amount of moisture, some solvent exchange or hydrogen exchange takes place, or as an impurity, CdCl3 may contain little amount of CHCl3, and that hydrogen, CHCl3 hydrogens, will appear at 7.27. So the primary standard is actually the TMS, And along with that, to correct the NMR scales, we can use this CHCl3 peak at 7.27 as the secondary standard. So if we add more and more electronegative elements, then there is an added effect on the chemical shift values. The other incident is, if we increase the distance between the electronegative atom and the hydrogen under question, we know that the inductive effect will get decayed or reduced if we increase the distance. So if bromine is connected to the carbon which carries the hydrogen under examination, the value is nearly 3.3. If we move the bromine to the next carbon, the value gets reduced to 1.69. So the electron withdrawing effect of bromine is reduced. If we move bromine again to the second carbon, the value gets reduced to 1.25. So the presence of electronegative elements will greatly influence the chemical shift value. They will remove or they will withdraw the electron density from the CH bond. So the hydrogens are de-shielded. And the de-shielding results in higher resonance frequency at the given B0 value. Another effect is anisotropic effect due to the presence of pi bonds. And this effect is more pronounced in benzene rings or aromatic rings. If you consider the benzene ring, we know that it is a planar molecule. And the pi electron cloud is above and below the plane of the molecule. And there is a closed loop of pi electrons. So we can mark the movement of the pi cloud as a blue ring above and below the benzene ring. And the magnetic field produced or induced is perpendicular to the movement of the electrons or this ring current. And that green lines represent the magnetic lines of force. See, at the center of the benzene nucleus, the induced field is opposite to the applied field B0. But when the magnetic lines of force reaches near hydrogen, the induced field and the external field are aligned. So those hydrogens will experience a slightly higher magnetic field. That is a de-shielding effect. So aromatic hydrogens Because of this ring current, they are de-shielded. And for simplicity, we can represent the shielding and de-shielding area with the help of cone. See the pink colored cone that represents shielding cone. We can put a plus sign that represents the shielding. The other regions. So the shielding cones are above and below the plane of the benzene ring. But we know that all hydrogens in the benzene ring are in the plane, the horizontal plane. So those hydrogens are de-shielded. But in the case of cyclophanes, some CH2 groups are above the plane of the benzene ring. So they will come under the shielding cone. And in that context, those hydrogens will be shielded and they are near TMS or sometimes below, or sometimes they may exhibit negative chemical shift values. Another situation is the chemical shift of vinyl protons. They appear in between 5 and 6 ppm. In the case of aromatic protons, the chemical shift value is from 6 to 8 or 9. But here it is slightly less. The reason is that here there is no ring current. The electrons are moving, but not as intense as that of aromatic system. So the induced field, which is aligned with the applied field near the hydrogens, are less compared to aromatic system. That is the reason why the vinylic protons have less chemical shift value compared to aromatic hydrogens. If we consider acetylenic protons, it's nearly 2.5. Here the carbon is in sp hybridized state. We know that sp hybrid carbon is more electronegative compared to sp2 or sp hybrid carbons. So the normal expectation is that these hydrogens are, we know acetylenic hydrogens are acidic in nature. So these hydrogens are highly de-shielded, because of the electronegative nature of sp hybridized carbon. But the actual observation is just opposite to that. It is not that much de-shielded. It's not that much de-shielded. We can explain this with the help of the symmetry of the molecule. Acetylenic systems has cylindrical geometry. So if we analyze the direction of the induced magnetic field, just as we have done in the case of benzene ring as well as vinylic systems, here we can see that near the acetylenic hydrogens, the induced field is opposite to that of applied field. Or in terms of shielding cone, acetylene hydrogens are in the shielding cone or shielding area. That means they are more shielded than the hydrogens of benzene as well as vinylic systems. That's why even though sp hybridized carbon is more electronegative compared to sp2, acetylenic protons appear nearly delta 2.5. Another example is aldehydic protons. CH3 CHO acetaldehyde. That hydrogen appears nearly at 9.3, 9.5 range. See, the carbon is attached to oxygen only. It's not a more electronegative compared to, it's not much electronegative element. It is less electronegative compared to fluorine. We have seen the case of CH3F. That CH3 hydrogen appears at 4.2. But here in the case of aldehydic hydrogen, it appears, or those hydrogens are much more de-shielded compared to CH3F. How we can explain this? Okay, there are two effects. One is the electronegative influence of oxygen attached to the carbon bearing hydrogen. Yes, that is represented in terms of that dipole vector. There is an electron withdrawal from CH bonding to oxygen. And that is not alone will explain this anomalous de-shielding of aldehydic hydrogens. We have to consider the anisotropic effect as well. This is very similar to that of the vinylic systems. So, along with the de-shielding of the electronegative oxygen, anisotropically, magnetic anisotropic effect also will operate here. See, near the hydrogens, aldehydic hydrogen, the induced field is aligned with the applied field. The induced field is aligned with the applied field. So, by electronegativity effect, that aldehydic hydrogen is de-shielded. By magnetic anisotropy, also aldehydic hydrogen is de-shielded. So the added effect is they are greatly de-shielded. Another parameter or factor which influence the chemical shift value of a NMR active nucleus is hydrogen bonding. So if we consider the chemical shift value of alcoholic hydrogen, it varies from 0.5 ppm to 5 ppm. And that makes so many complexities while analyzing the NMR spectra which contains these types of hydrogens. And we already mentioned that in such cases, to confirm the presence of OH hydrogens or NH hydrogens, the usual technique is deuterium exchange. Now let us see how this hydrogen bonding influence the chemical shift of hydrogens. See the figure? The hydrogen bonding actually will lengthen the OH bond. The same thing is explained in the case of IR spectroscopy as well. As the bond gets lengthened, what it means? The electron density around hydrogen gets diminished, and therefore that hydrogen, we can consider that hydrogen is de-shielded. The hydrogen is de-shielded, and the signal, NMR signal, is shifted downfield. And why that hydrogen bonded hydrogen appears in between 0.5 and 5 ppm, a wide range? It is because the extent of hydrogen bonding may be different in the given sample. That depends on several factors. The presence of protect solvents, or the concentration, temperature, so many factors. That's the reason why the alcoholic hydrogen or amino hydrogens appears in the NMR spectrum in between 0.5 to 5 ppm. So to ensure the presence of these types of hydrogens, they are actually exchangeable. They are known as exchangeable hydrogens. We used to exchange, or we used to add few drops of D2O to the sample and shake it well. Then deuterium exchange will take place, and we know that the gyromagnetic ratio for deuterium is different from hydrogen. So the deuterium resonance position is beyond the NMR scale of H1. So the peak may either disappear or the intensity may get reduced if the sample contains such exchangeable hydrogens. Another case is carboxylic acids. The hydrogens of carboxylic group, COH hydrogens, appears in between 10 to 12 ppm, very far downfield or highly de-shielded. Why? We are conducting the NMR experiment in organic solvents, non-polar organic solvents. So we know that in non-polar organic solvents, usually these carboxylic acids will form dimers, and where we can see strong hydrogen bondings. And that's the reason why those hydrogens are highly de-shielded. Not only hydrogen bonding, the electronegative influence of COO grouping. So these two effects, the electronegative effect of COO group and the hydrogen bonding, will make the carboxylic hydrogens appear at very far downfield in NMR scale. Another beautiful example is methyl salicylate. See, from the structure itself, you can see that there is a very good hydrogen bonding, and it forms a 6-membered transition state like structure. So this alignment will make the phenolic hydrogen absorption at nearly 14 ppm. 14 ppm. Almost the same is the case with enolic hydrogens. They also appear at 13 to 15 ppm. So in summary, what are the factors affecting the chemical shift values? Nu is equal to gamma by 2 pi B0 into 1 minus sigma. Gamma, gyromagnetic ratio, it's a constant for a given nucleus. 2 pi, another constant. B0, the applied field. If the applied field is the same, then the chemical shift value or the resonating frequency depends on sigma. That is a parameter which directly connected to the environment of a particular hydrogen. I repeat, this dependence of nu on the structure or the environment of the hydrogen nucleus is the ultimate reason for the importance of NMR spectroscopy in organic chemistry or in structural elucidation experiment.